At the end of the 19th century, in a small river town in Vermont, a machine tool maker did something many businesses of the era would have considered reckless. It placed almost all of its strength behind a single, controversial design. The man behind that decision was James Hartness, a young engineer recently arrived in Springfield, with no great reputation, no long record of success, and no guarantee that customers would accept what he was proposing. If the market rejected the machine, Jones and Lamson would have little else to fall back on. The company risked not only a product line, but its finances, its customers, and perhaps its future. But history moved in the opposite direction. That machine did more than save the company. It became the foundation for a network of precision engineering businesses that helped turn Springfield, Vermont, into one of the most influential machine tool centers in the United States. As always, before we turn back the clock, if you enjoy stories about the machines, factories, and industrial brands that shaped the modern world, leave a like and subscribe to the channel. The story actually begins before Hartness ever arrived. By the middle of the 19th century, Windsor, Vermont, had already become associated with Robbins and Lawrence, one of the important workshops in the early development of the American machine tool industry. Shops like these built the milling machines, lathes, fixtures, and gauges needed to manufacture firearms and other products that required interchangeable parts. Through changes in ownership and company names, one branch of that tradition eventually became Jones and Lamson. By the late 1880s, the company was producing a variety of equipment, but it still lacked a single product powerful enough to define its reputation. In 1888, Jones and Lamson moved from Windsor to Springfield. This was more than a change of address. It separated one group of machinists and engineers from the old Windsor works, while those who remained in Windsor continued to develop their own lines of machinery. In the years that followed, Windsor and Springfield would exchange people, ideas, and companies again and again. So when Hartness entered Jones and Lamson the next year, he was not starting from a blank page. He was stepping into a machine tool tradition that had been evolving for decades. What he did was choose one branch of that evolution and push it to its limit. James Hartness was born in 1861 in Schenectady, New York, and grew up in Cleveland. He did not follow the typical path of an academically trained engineer. As a teenager, he learned his trade in machine shops, working directly with parts, tools, and the small errors that no drawing could hide. Over the following years, he moved through a series of jobs from shops in Ohio to Winsted and Torrington, Connecticut. At Union Hardware, he rose from toolmaker to foreman and then became involved in invention work. By 1886, he had begun filing patents. The winter of 1888 to 1889 brought another round of movement, with short periods of work at Pratt & Whitney in Hartford, Eaton, Cole, and Burnham in Bridgeport, and a shop in Pennsylvania. Looking back, those short jobs seem less like instability and more like a search. Hartness was carrying an idea in his mind for a different kind of turret lathe. What he needed was a company small enough to change direction, but capable enough to build what he imagined. Springfield gave him that opportunity. In the spring of 1889, Hartness joined Jones and Lamson as superintendent. He was only 27 years old. The moment Hartness arrived in Springfield was also a moment when American industry was changing rapidly. Manufacturing no longer needed only one correct part. It needed hundreds, then thousands of parts, made correctly in the same way. Railroads, sewing machines, electrical equipment, firearms, and especially the emerging automobile industry were pushing machine shops toward a new limit. On a traditional lathe, the machinist had to change tools, reset the work, and check the result after each operation. A highly skilled worker could do this extremely well, but the output of an entire factory was still limited by the number of people who had enough experience to repeat those operations accurately. The turret lathe was created to reduce that bottleneck. Instead of mounting one cutting tool at a time, several tools could be arranged on a turret and brought into use in sequence. A workpiece could be turned, drilled, reamed, or threaded in a single setup. The great value of the turret lathe was not simply that the turret rotated. It was that the order of work could be built into the machine itself. Setup time fell, errors caused by repeated handling were reduced, and the operator no longer had to recreate the entire process from scratch for every part. But the turret lathes common at the time still had weaknesses. Their turrets were high, heavy, and positioned far from the cutting zone. Hartness saw that weakness as an opportunity to rethink the entire layout. Hartness replaced the tall barrel-style turret with a large, flat disc mounted low on the carriage. At first glance, the change looked simple, but it affected rigidity, visibility, and the way the operator interacted with the machine. With the tools closer to the spindle center line, cutting forces passed through a shorter and stronger structure. That reduced the tendency toward vibration and deflection. The upper part of the machine was also more open, allowing the operator to see the workpiece and the cutting area directly instead of working around a high turret block. More importantly, the design made it possible to handle long cuts and relatively slender parts more effectively, a problem Hartness believed existing machines had not solved well enough. During development, he also found old company sketches showing a similar mechanism drawn decades earlier by Frederick W. Howe. That detail matters. Hartness did not invent every principle from nothing. He recognized an idea that had been ahead of its time, then combined it with the production needs of the 1890s. This is a pattern that appears again and again in machine tool history. A mechanism becomes revolutionary only when technology, market demand, and factory organization finally meet at the right moment. On January 9, 1891, Hartness filed a patent application for a machine for making screws, describing a turret lathe capable of handling a wider range of work and better supporting long, slender pieces. Patent number 457,967 was granted on August 18th of that year. But a patent only confirms ownership of an idea. The market decides whether that idea is worth anything. In May 1891, American Machinist gave significant attention to the new machine, and that same year Jones Lamson began selling the flat turret lathe commercially. At the same time, Hartness pushed the company toward a bold choice. Instead of spreading its resources across many machine lines, Jones and Lamson would focus almost all of its effort on the flat turret lathe. Inside the company, this was the real point of controversy. A broad catalog at least allowed one weak product to be offset by another. Concentrating on a single design meant every improvement, every technical problem, and every customer reaction would be magnified. Hartness had a multi-year contract that gave him enough protection to endure the early resistance. The flat turret lathe sold. More importantly, every machine that entered a customer's shop became a real-world test that competitors could not easily dismiss. Shop owners did not have to believe advertising claims that the design was more modern. They could count the reduction in setups, watch a sequence of operations run continuously, and calculate the cost per part. This was the special advantage of a machine tool. Jones Lamson's product was both a manufacturing device and a demonstration of productivity. By the mid-1890s, the signs of expansion were clear. A Springfield history published in 1895 recorded that Jones Lamson employed about 150 workers and had agencies in London, Paris, and Dusseldorf. The machine, proposed only a few years earlier by a young superintendent, had begun to move beyond the local market. Yet Hartness did not respond by launching a flood of new products. For nearly a decade, Jones Lamson continued selling mainly the same type of flat turret lathe, in one size. Each round of feedback from customers returned to the shop and improved the same platform. The company's advantage accumulated instead of being scattered. The success of the machine also changed Hartness's place inside Jones Lamson. He began as superintendent, became manager in 1893, and by 1900 had become president. This was the period when the idea of focus moved from a product decision into a way of organizing the company. When a firm concentrates on one main machine platform, its design team comes to understand its limits more deeply. Its manufacturing department repeats similar assemblies often enough to standardize processes. Its sales force can speak with customers about specific work rather than simply hand them a general catalog. Hartness also wrote and spoke about the machine shop as a system, not merely as a collection of machines standing side by side. He was interested in the path of the workpiece, the movements of the operator, the preparation of tooling, and the way skill could be transferred from an individual person into a repeatable method. He would later organize these ideas more clearly in his 1905 book, Evolution of the Machine Shop. But before that book appeared, an even more important consequence had already begun. Talented engineers working around Hartness did not always remain at Jones Lamson. Some of them would take specialized problems outside the company and build firms of their own. Edwin R. Fellows was the first and clearest example. Fellows worked with Hartness during the early years at Jones Lamson and helped develop the flat turret lathe. But his interest gradually shifted toward another problem, cutting gears. In 1896, Hartness encouraged Fellows to establish an independent business in Springfield rather than pull Jones Lamson into another product line. From that decision came the Fellows Gear Shaper Company. Fellows received a patent for his gear-shaping machine on March 30, 1897. The new mechanism used a cutter and a workpiece, moving in a defined relationship to generate the tooth profile. It turned a difficult, hard-to-repeat task into a machine-controlled process. The timing was nearly perfect. In 1898, one of Fellows's machines was sold to the Electric Vehicle Company. Later, automobile makers such as Packard, Oldsmobile, Cadillac, and Buick became customers. As the automobile moved from experiment to mass production industry, transmissions and drivetrains required growing numbers of accurate gears. Fellows did not compete directly with Jones Lamson. He opened a new point in the same manufacturing chain. Springfield now had a second company, known for solving one narrow problem in great depth. When Fellows left, Jones Lamson needed a new generation of designers. In 1897, William Leroy Bryant, then an engineering student at the University of Vermont, joined the company as an assistant draftsman. Bryant worked closely with Hartness on turret lathe designs with a cross-sliding head, and by 1900 he had become head draftsman. At the same time, the flat turret lathe itself did not stand still. After nearly a decade of accumulated experience, Jones and Lamson introduced a more powerful version in 1903, heavier and capable of larger work than the early machines. It was evidence of the advantage of not replacing a product platform every few years. The company could extend the same principle into heavier work without throwing away everything it had already learned. But Bryant saw a limit beyond turning. When parts had been hardened, or when holes, outside diameters, and end faces required high-precision finishing, grinding became necessary. Rather than treating this as a reason for Jones and Lamson to create a new division, the Hartness model again pointed in another direction. Let the person with the idea build a specialized company of his own. Another branch left Springfield and moved back toward Windsor. George O. Gridley had worked under Hartness at Jones and Lamson, originally even as a clerk before moving more deeply into machinery. In 1899, Gridley became superintendent of the Windsor Machine Company, operating in the old works associated with Robbins and Lawrence. There he developed an automatic turret lathe and then pushed the idea further into multi-spindle machinery. In 1907, Gridley introduced a 4-spindle design in which several workpieces could occupy different machining positions during the same cycle. If Hartness's flat turret lathe reduced tool-changing time on one workpiece, the multi-spindle automatic solved a different problem, producing many parts in succession with even less operator intervention. In 1916, Windsor Machine was sold to National Acme, and the line became part of the later Acme-Gridley name. Significantly, this direction did not require Jones and Lamson to manufacture the machines itself. An idea moved out of the parent company, returned to Windsor, and formed its own branch of automation. The industrial network around Hartness expanded, not because one company absorbed everything, but because specialized knowledge kept separating into new enterprises. By the beginning of the 20th century, Hartness had achieved a position that would have seemed impossible 15 years earlier. He was president of Jones and Lamson. The flat turret lathe was known in international markets. Around him, a group of engineers was beginning to create new businesses of its own. In 1904, Hartness House was built in Springfield. It was his home, but over time, it also became associated with his other technical interests. In 1905, Hartness published Evolution of the Machine Shop. The book was not merely about the shape of a lathe. It asked a broader question: how does a shop evolve when production increases and skill must be transferred from individuals into machines, tooling, and process? This thinking explains why Hartness repeatedly chose specialization. If each manufacturing problem has its own particular combination of design, tooling, and method, then a company trying to make every kind of machine can easily remain only good enough. But a group that lives with one problem has the chance to accumulate thousands of small improvements. That logic was already taking physical form in Springfield. J&L with turret lathes, Fellows with gear shaping, Windsor with automatic machines. The largest missing piece was grinding. Bryant had been pursuing grinding since the early 1900s and filed his first patent related to the design in 1902. His key idea was to bring the concept of chucking work from the lathe to the grinder, hold the part in one setup, then finish several accurate surfaces from the same reference. Bryant's design used 3 independent grinding heads to work on internal diameters, external diameters, and end faces. On March 29, 1909, the Bryant Chucking Grinder Company was founded in Springfield with financial support from Hartness. Hartness became the new company's first president. In 1910, a factory of about 20,000 square feet was built across from J&L, and 9 machines were delivered to Ford and Cadillac that same year. This was a clear sign of where the Springfield cluster was heading. The turret lathe enabled rapid shaping. The gear shaper solved gears. The automatic lathe raised output. The grinder brought critical surfaces to final size. These companies were not copies of one another. Each held a different segment of the machining chain, and all of them benefited as the American automobile industry accelerated. Outside the factory, Hartness pursued a field that seemed unrelated: astronomy. Around 1910, he completed a special turret telescope on the grounds of Hartness House. Instead of placing the observer outside with the telescope, Hartness arranged the observing position in a protected space and developed a way to bring light to the user through an optical system. The underground rooms and tunnels around the house later became connected with Springfield's amateur telescope-making community. This detail matters not because Hartness needed another hobby in his biography. It shows that he was living in 2 technical worlds at once: precision mechanics and optics. In the machine shop, he cared about holding tools, workpieces, and motion in stable geometric relationships. In the telescope, the problem became light, lenses, mirrors, and the ability to see things too distant or too small for the unaided eye. Those 2 lines of thought would eventually meet in an entirely new device for the machine shop. But before that happened, Springfield and Hartness would pass through a larger period of upheaval, World War, and the rise of aviation. In 1914, Hartness became president of the American Society of Mechanical Engineers for the 1914-1915 term, a sign that his influence had moved far beyond Jones and Lamson. During this same period, he pursued aviation, learned to fly, and received a pilot's license. Aircraft were still young technology. The Wright brothers' first flight had taken place only a little more than a decade earlier. To Hartness, aviation was another systems problem like the machine shop, but even more unforgiving. Weight, reliability, engines, materials, and standards all had to work together. During the First World War, he was assigned public roles connected with organization, resources, and aviation. These included serving as Federal Food Administrator for Vermont and participating in the Inter-Allied Aircraft Standardization Commission in London and Paris. These years pulled Hartness beyond the scale of a single workshop. They forced him to think about standardization at the national and international level. When thousands of machines, engines, and parts had to be produced quickly for war, the question, "Are these 2 parts truly the same?" was no longer an internal factory issue. It became a supply chain problem. Even during this period, Springfield continued producing new companies. Fred Prescott Lovejoy had worked at Jones and Lamson and became a specialist in small tool design. In 1916, he founded Lovejoy Tool Company in Springfield, focusing on cutting tools rather than complete machine tools. Hartness again provided financial support for the new business. That same year, Windsor Machine, with its Gridley line, was acquired by National Acme, placing the multi-spindle design inside a larger organization. At Bryant, wartime demand drove expansion. By 1917, the company was running 3 shifts a day. In only about 2 decades, the Springfield-Windsor region had built a chain of capabilities that did not exist there in 1889: turning, automatic turning, gear shaping, grinding, and cutting tools. This expansion did not happen because of a master plan drawn in advance. It happened because each engineer identified a new bottleneck in production and was encouraged to separate from the parent company to solve it. This is where Hartness's strategy of one company, one deep specialty became larger than Jones and Lamson itself. He accepted the loss of talented people from his own payroll in exchange for a stronger network of companies around him. After years spent thinking about how to make parts faster, Hartness turned his attention to another question: how to inspect the shape that the machine had just produced. The problem was especially difficult with screw threads. A thread is not defined by diameter alone. Lead, angle, profile, and surface condition all affect whether the part will fit and function. Contact gauges could check some dimensions, but they did not allow the inspector to see the entire profile in a single image. Around 1919, Hartness and Russell W. Porter developed the first commercial optical comparator. Porter was an engineer, artist, and explorer with optical experience. Hartness brought deep knowledge of machine shops and inspection. Instead of touching a probe to a few points, the comparator projected a magnified image of the part onto a screen, where it could be compared with a standard outline. A tiny error in profile became a large, visible difference. This was an important shift. Inspection skill was transformed into a visual, repeatable act. Around the same time, Hartness continued to support aviation in Springfield. The local airport opened in 1919. Mechanics, optics, and aviation might seem like three separate interests. For Hartness, they revolved around the same question: how can precision be designed, controlled, and verified? Hartness did not stop with engineering. He had served on the State Board of Education from 1915, and in 1920 he entered the race for governor of Vermont. In the November election, Hartness won 67,674 votes, about 78% of the total, and began his term as governor in January 1921. He served one term, leaving office in early 1923. What is notable is that this political chapter was not completely separate from the rest of his life. Hartness brought into government the same concerns that had followed him from the machine shop: industrial development, the training of people, and the creation of conditions that would allow manufacturing capability to remain in Vermont rather than flow to larger states. During his term, Vermont also saw the first woman elected to the state legislature. After leaving office, Hartness did not build a long political career. He returned to technical and business activities. That makes his governorship feel like a brief branch in a life still centered on production. And in the years immediately after his term, the optical measuring device he had begun with Porter would move toward patent completion. Jones and Lamson commercial literature shows that the Hartness screw thread comparator was being offered by the company at least by 1924. On May 21, 1925, Hartness and Porter filed a patent application for the optical comparator. U.S. Patent 1,703,933 was granted on March 5, 1929. The purpose was described very specifically: to inspect screw-threaded elements and detect errors in diameter, lead, form, profile, and even surface condition. The device was designed to be compact enough for ordinary shop conditions. That is what made the comparator different from an optical experiment in a laboratory. It had to live next to machine tools where oil, chips, production rhythm, and time pressure were daily realities. If the flat turret lathe of 1891 transferred part of the machinist's skill into the arrangement of the machine and tools, the comparator did something similar for inspection. It turned a difficult geometry into an image that different people could read against the same standard. More than 3 decades after his first great gamble, Hartness had moved from making parts quickly and repeatedly to proving that those parts were truly the same. The two inventions stood at opposite ends of the same manufacturing process. By the end of the 1920s, the most important thing about Springfield was no longer Jones and Lamson alone. Fellow's gear shaper had tied its fate to the growth of the automobile industry and become a major name in gear production. Bryant helped turn grinding from a toolroom activity into a process suited for the mass production of precision parts. Lovejoy built capability in cutting tools. In Windsor, Gridley's designs lived on through the Acme Gridley line. J&L maintained its turret lathes while also bringing the comparator into metrology. The factories gathered in a small region created a special labor market. A draftsman, toolmaker, or machinist could move from one company to another and still work within the same culture of precision. Knowledge, therefore, did not exist only in patents. It existed in how a tool was ground, how a machinist heard vibration in a machine, how a setup was prepared, and how an error was recognized before it became thousands of defective parts. Springfield gradually became associated with the name Precision Valley. What matters is that this cluster did not form because of an advantage in raw materials. It formed through the accumulation of people and specialized knowledge, something harder to move than steel and harder to copy than a drawing. James Hartness died on February 2, 1934, in Springfield. By then, his career had moved far beyond the image of a 27-year-old superintendent walking into Jones and Lamson in 1889. He had been president of J&L, president of ASME, governor of Vermont, a promoter of aviation, an amateur astronomer, and co-inventor of the optical comparator. The American Precision Museum credits him with about 120 patents in the United States and 48 foreign patents. But the number of patents is still not the best measure of Hartness's influence. The companies he helped make possible continued to grow after his death. Fellows expanded strongly in gear machinery. Bryant became an important grinder manufacturer. Lovejoy continued in cutting tools. Automatic machines with origins in Gridley's work became widely used. When the Second World War pushed demand for machine tools to enormous levels, Springfield already had a system of factories, engineers, and machinists built over decades. Hartness did not live to see the full scale of that period. But the workforce, the industrial base, and the philosophy of specialization he helped create were already in place before the war began. Looking back from the end of the story, the gamble of 1891 was not simply that Jones and Lamson bet on a flat turret lathe. The larger gamble was a belief about how technical progress happens. Hartness believed that a problem important enough deserved a group of people focused on it for so long that they would understand it more deeply than anyone else. He applied that belief to the turret lathe. But when Fellows wanted to solve gear cutting, Bryant wanted to solve grinding. Gridley wanted to automate production, and Lovejoy wanted to specialize in cutting tools. Hartness did not try to force all of those ambitions into departments of J&L. He allowed them to separate. The result was that Jones and Lamson did not become an empire that made every kind of machine. Instead, Springfield became a place where many specialized companies stood side by side, creating an industrial capability that no single firm could easily have built alone. In the end, Hartness went one step further, from manufacturing to measurement, from creating shapes to confirming those shapes with light. That is why his story is larger than the story of a lathe. The flat turret lathe was the most visible starting point, but the real legacy was the chain reaction it set in motion. One successful design created a stronger company. That company trained talented people. Those people left to build new firms. And those firms created the markets, skills, and standards of an entire region. A single machine does not build an industrial valley by itself, but sometimes the right machine, the right person, and the right decision at the right moment can begin the process. If you enjoyed this video, like, subscribe to the Gear Archive, and leave a comment with your thoughts. Thanks for watching, and I'll see you in the next one.